In this video, I want to take a look at the properties of the dot product. This will allow us to be able to, well, do algebra with expressions that involve the dot product. Now, we already have one property that we've seen, namely that the dot product is the norm of the vector squared, or the length of the vector squared. I think in previous videos we wrote it as the length is the square root of the dot product of a vector with itself. So yeah, the dot product of u with u is equal to the length of u squared. Right. Now, here's some other algebraic properties. Right? This one I think we've already seen, that the dot product is commutative, so u dotted with v is v dotted with u. There is a distributive property over vector addition. So we know how to add vectors, and we know how to dot vectors together. Okay? So the dot product of u with the sum v plus w is the same as the dot product of u with v plus the dot product of u with w. It distributes just like multiplication does. Also, there's this, well, kind of an associative property, but if you take a dot product and then multiply that by a scalar, that would be the same thing as multiplying the scalar by the first one and then taking the dot product. Notice that there's not an associative property. You don't have u dotted with v dotted with w with two of them in parentheses and then you move the parentheses. The thing is, you can't dot three vectors together, because as soon as you dot two of them together, the result is a number. And then that number doesn't get dotted with a vector. That number might be multiplied times a vector, you know, like a scalar multiple. But you don't have an associative property because you never dot three things together. Anyway, here we go. There's that one, and then we have that the dot product of a vector with itself is always greater than or equal to 0, and that dot product of a vector with itself is equal to 0 if and only if the vector is the 0 vector. Now, that should be a 0 vector. That's not just a 0. Hang on a minute. I took a moment to change that because this is an important point here, that the dot product gives you a number as an output. So the 0 here is different than the 0 here. This is the number 0. The dot product equals the number 0 if and only if the vector is the 0 vector. Right? And remember, in algebraic terms, the 0 vector is a list of zeros. So 0, 0, 0 in R3, or whenever Rn is, you got a list of n zeros, and that's the 0 vector. Now, I want to point out that I call these the inner product properties. I've mentioned the word inner product in previous videos. If we had a second quarter of this linear algebra class, we would get into inner products and inner product spaces. And the definition of an inner product is it's an operation that takes two vectors in your vector space and somehow combines them to give you a number as an output. And if that operation satisfies these 5 properties, it's called an inner product. Okay, so this first theorem, just the stating or proving that these properties are satisfied by the dot product, is just proving that this is an inner product. Okay. Now the book never mentions that, but they've taken great pains to set this up, that they didn't just list all the properties, they list 5 of them first, and they come back and list a bunch of others. It's like, why did they separate those 5? Because these are the 5 that make it an inner product. And this is called, of course, the Euclidean inner product. So I'll give a proof just one of these parts. I think some of the homework asks you to prove others, but I'll do number 3 here. So k times u dotted with v is k times there's u dotted with there's v, except that it looks like a bunch of u's. Yeah, that looks better. I'm going to have to talk to my editor, my proofreader, and make sure that that he does a better job of setting these files up here. Anyway, k times the quantity u dotted with v. Of course, the dot product would just be u1 v1 plus u2 v2 plus and so on up to un vn. Now this is just all real numbers. This is a multiplication of k times the sum. So the distributive property allows me to distribute the k into each one of those pieces. Now, each one of those terms in that sum now is just a product of 3 real numbers. And the product of 3 real numbers satisfies an associative property. So rather than multiplying u1 and v1 together first and then multiplying by k, I could multiply the k times the u1 and then multiply by the v1 afterwards, and likewise in each of those others. So this, going from this step to that step, is just the associative property of multiplication of real numbers. And then I'm saying, oh, but look at this now, looks like this dot product with ku1, ku2 up to kun dotted with, and again, my editor is not doing his thing here. These should be v's over here. I'll have to have a talk with him. Yeah, there we go. Now, so this dot product with ku's and the vector, all the stuff from v here, and then of course the k can be factored out of that. That's how you do scalar multiplication in Rn. And so what I have is ku dotted with v. Okay, so there's the proof of number 3. Proofs of the other ones are similar. You just look at what the, write out each one and see that you get the same thing on each side. Write it in terms of the components of the vector and see that the left-hand side is equal to the right-hand side when you do both calculations. Okay. Now, next theorem is just more properties. If u, v, and w are vectors in Rn, and k is a scalar, that is a real number, then we have these properties. If you take u and dot it with the 0 vector, that's the same thing as u dotted with the 0 vector on this side, which is 0. Again, notice this is the real number 0, where these were 0 vectors over there. The distributive property works on the right-hand side as opposed to the left-hand side, which we saw earlier. Now, this maybe isn't very surprising because, of course, we already know that the dot product's commutative, so you can swap sides. Anyway, each one of these properties is a consequence of the first 5. Right? In fact, the first 3, really. Except for the first one here. This one you just look at what happens when you got all zeros times all those u1, u2 up to un, right? That those are all going to be zeros, and then you add them together to get 0. But these 2, 3, 4, and 5, you don't need to get into the individual entries in the vectors because you can just use the properties of the previous theorem to show that these are true. Okay. But what these all do now is they allow us to do algebra with the dot product. So for instance, here is a product of two combinations of u and v, 3u plus 2v and u minus 4v, and I'm going to dot the two together. Okay, this is one vector, that's another vector, and I'm taking the dot product. Well, I can use all these properties in the 5 listed above to help me do that algebra. Because, for instance, I know that there's a distributive property. So this 3 plus 2v, 3u plus 2v, can be distributed to be dotted with both of those, and that's what I did. Here's the 3u plus 2v dotted with the u, and then the 3u plus 2v dotted with the 4v, and there was a minus sign in between, so I got the minus sign. The fact that I've got this property here, number 5, and the one I proved up above, essentially means that I don't need the parentheses in there, that it doesn't matter whether you dot it first and then multiply by k, or multiply the first one by k, or multiply the second one by k, and then do the dot product. It's all the same. So I'm not worried about when I have here 3 u dotted with u, is that 3 attached to that u, or do you do the dot product first and then multiply by the 3? All those properties up there say, it doesn't matter, do it either way. Okay. So I'm playing a little fast and loose with that because I know I can. Properties tell me I can. Right? So there was that first distribution, and now I'm going to distribute again. That is, I can distribute this u over that sum. So this would be 3u dotted with u and 2v dotted with u. So that's that first part there. And then minus what I get when I distribute this into those two. So there's the 3u dotted with the 4v and the 2v dotted with the 4v, and the minus sign distributes in as well. So I got minus, minus. Now, these constants can come out in front. So for instance, here the 2 and the 4 become an 8. But then v dotted with v is the length of v squared. Likewise, the u dotted with u is the length of u squared. The two things in the middle, actually, before I do the two things, though, what I want to say is the result of the two. Actually, I did the distributed property three times, right? I distributed in here, and then I distribute each of those in. The result is essentially FOIL. At the first here, this was the first dotted with the first. This was the insides. So this was the inside, and then the -3, 4, that's the outside, and then the 2V, 4V, those were the last. So this is, and it's not FOIL, I guess it's file. First, insides, outsides, last. Just like you would multiply a binomial together. The algebra is the same because the properties of this dot product are essentially the same as the properties of multiplication. It works with vector addition the way that real number multiplication works with real number addition. So the way that you do the algebra is just the same as what you would have done with numbers. Okay. Now the last thing I want to say here is that the u dotted with v and the v dotted with u are the same. So so I can turn them around to both look the same. I have both as u dotted with v here. And so then I have +2 and -12 of those things for a total of -8. And so this product, this dot product here, can be rewritten as this. Why you would want to do that, I don't know what problem you're working on. The point at this stage is just what are the properties? What is the algebra that we can do? Okay. Now, the next thing I want to take a look at is the so-called Cauchy-Schwartz inequality. It has other names as well, depending on what part of the world you're from, and the math that I learned, the math that's mainly in the book, although the book does it fairly, at least it tries to grab other names out of the rest of the world. But it's mainly based on European math history as opposed to the Russians or the Chinese or the Arabs, whatever. There's a lot of people doing math in different parts of the world, and the people don't necessarily get the credit for the work they did because it's fairly European-centric in our textbooks. But Cauchy-Schwartz, this is kind of fun for me just because Schwartz is one of my mathematical ancestors. That is, I have a PhD and I had a PhD advisor. My advisor had an advisor and he had an advisor and an advisor and an advisor. And you go back, I don't know, about 6 generations, and Hermann Schwartz is the advisor of my advisor's advisors, advisors, whatever. You go back a couple generations from him and you get back to Gauss. But anyway, the Cauchy-Schwartz inequality. This is one that I think is just vastly overrated, but I understand why, and I'll explain. The theorem says if u and v are vectors in Rn, then the absolute value of the dot product is less than or equal to the product of the lengths. Okay. Now, to me, this is like, well, duh. Of course it is, right? Here's my proof, my one-line proof. The dot product is the product of the lengths times the cosine of the angle in between them. So if I take the absolute value of both sides, these are both positive, so it's just a matter of the absolute value of cosine. Well, I know that cosine of the angle is somewhere always between -1 and +1. So what am I multiplying the product of the lengths by? I'm multiplying it by something smaller than 1, bigger than 0. It's possibly as big as 1 and possibly as low as 0, but never more than 1. Right? It's never going to get bigger than the product of u and v. It's going to be less than that. So this just seems like, sure, of course, it's because you're multiplying by cosine. It gets smaller. Now, I think the reason why this is a little more valuable than what I put on it is that the geometric definition of the dot product is, well, it's geometric, right? It's really 2D or 3D. Our textbook, for instance, does not count this as legal proof in R4, right? R5, whatever. So it's looking only at the algebraic definition to try to prove this statement, okay? And then there is a proof given in the book eventually. But to me, it's intuitive. The dot product is the product of the lengths times the cosine, and the cosine is always less than 1, so you're getting a smaller answer with the dot product than if you just multiply the two things together. Okay. Now, the triangle inequality. The triangle inequality. I need to draw a picture. The triangle inequality. There's two versions of it here, one in terms of vectors and one in terms of distances. So the first version of it is saying if you've got the vector u and you add to it the vector v, then u plus v, of course, would be this going from here to there. And the theorem says that the length of the sum, so this length, is less than the sum of the individual lengths. That if you want to go from here to there, the shortest distance is the straight line path, right? So this one side of the triangle is shorter than the sum of the other two sides. That's why it's called the triangle inequality. One side is shorter than the other two. Okay. Likewise, with distances, you got three vectors. So here's the vector u, here's the vector v, and here's the vector w. And we're saying that the distance from u to v, this distance right here, is shorter than the distance from u to w plus the distance from w to v. Again, you're looking at one side of the triangle being shorter than the sum of the other two sides. Okay. Now, again, geometrically, I think that looks obvious. From the point of view of proof, and in higher dimensions, it's a matter of looking at, writing these lengths as dot products, right? That the length of u is the square root of the dot product of u with u. This is the square root of the dot product of v with v. And moving some things around and seeing that this length is indeed less than the sum of those two. Okay. And lastly, there's a theorem here that I'll admit to you, I never use it, but it's curious geometrically anyway. If this is the vector u and this is the vector v, then think of the parallelogram determined by those two. U plus v is the vector that is this diagonal, and u minus v is the vector, I guess, going this way. And what this says is that the sum of the squares of the diagonals, so this is the square of one diagonal, that's the square of another diagonal, it's equal to essentially the sum of the squares on all the sides, because it's u squared would be the length, would be the area of a square here, and v squared would be the area of a square there, but that's times 2, so you got this one and that one. So the sum of those four squares is the same as the sum of the two squares which are determined by the diagonals, right? Again, actually not again, because I don't think this one's obvious at all. It's very much like the Pythagorean theorem, but it's more general because it doesn't have to be a rectangle with right angles in it. It could be any parallelogram. But the proof, of course, would be write those as dot products and see what happens. So anyway, there's some algebraic properties of the dot product, and hopefully you can start to use them to do algebra